Alright, this is the second video for Chapter 6, so this will be the first part of Chapter 6, so videos 1 and 2 will be on the first part. So we're going to look at Introduction to Logarithms, Log and Exponential Equations, Part 1. The previous video we looked at log and exponentials only in graphing. So we have the conversion in the box there, log base b of x equals y, and then the double arrow is equivalent to, or if and only if, b to the y power is equal to x. So that might be something you want to make a flashcard. This right here being able to go between the log form on the left and the exponential form on the right. That's important. We'll talk a little bit about common log. That's log base 10. We mentioned it in the previous video a little bit when we graphed common log. And then also the natural log. That's log base b of x, which has an abbreviation of the natural log of x. And we did an example of graphing that. So we're going to do quite a few examples of converting from exponential to log and log to exponential, identify the base and the exponent and all that good stuff here. Okay, so first thing I'm going to do is go ahead and write log base b of x is equal to y is equivalent to b to the y power is equal to x. Alright, so we'll just have that up in front, and we're going to make a table. And in this table we'll identify a base, an exponent, the exponential form, and the log form. Alright, and what's going to happen is we're going to start with the exponential form or the log form, or maybe I give you the base and the exponent. We've got to fill in the rest of the table. So let's say I give you 2 to the third power is equal to 8. So we're going to identify here the base is 2 and the exponent is 3. So when we write this as log base b of x is equal to y, the base is 2, y is your exponent. So we have log base 2 of something is equal to your exponent. So the only other place the 8 can go is inside the logarithm. Okay. Now maybe you want to make a flashcard with something a little bit more concrete, so you could do a flashcard like this and then just make sure that all the points or all the numbers go in the appropriate locations there. Okay, so that is our first example. We'll take a look at another one. This time I'm going to give you the log form. So log base 5 of 1 over 125 is equal to negative 3. So we're going to identify the base of 5. Exponent is negative 3. So it is base to the exponent. So 5 to the negative 3. 5 to the third is 125. So if it's a negative 3, that's going to put it in the denominator. So 1 over 125 is your exponential form. Okay. And the homework assignments having to do with these, you might think it's a little overwhelming. They have a whole bunch of questions, but a lot of them are of this nature where you're converting from exponential to log or log to exponential form. So they're pretty simple once you get the hang of it. It does take a little bit of practice to start getting some of that muscle memory going, though. All right. So here I'll give you another one. Let's say we got 4 to the negative 3 is equal to 1 over 64. So this is an exponential form. We got to rewrite it as a log. Base is 4. Exponent is negative 3. So log base 4 of is equal to negative 3. So the logarithm is an exponent. So the 1 over 64 is going to go inside there. Okay, and we'll do one more. We're going to look at log of 10,000. Okay, so you see log there, you don't see a base. So you got to think, okay, is that base 10? Is that base e? This one's going to be base 10. If you have natural log, the ln, that's going to be base e. So this is base 10. So, and that's going to be equal to 4. So the base here is 10. It's a hidden base. We don't see it. But it is base 10. Okay. And the exponent is 4. So 10 to the fourth power is equal to 10,000. Okay. Alright, so we're going to look at some more examples of this. So we're going to rewrite the same thing. Log base b of x is equal to y is equivalent to b to the y power is equal to x. And we'll construct the same table so we can look at all different parts. So we're looking at the base and the exponent and the exponential form. And finally, the logarithmic form. Okay. So So what do we got going this time? All right, so this time they give us the base is e and the exponent is 7. And to make this look a little bit nicer, we're going to go ahead and say e to the 7th. And I went ahead and put this into my calculator, and I got it. It's approximately 1096, so you see that squiggly equals for the approximation. Okay, so then our base is e, and if it's base e, that means it's natural log. Natural log of the 1096 is going to be approximately equal to 7, and you can use your calculator and find the natural log of 1096, and I think you're going to get like 6.99999, something like that, really close to 7. So it's approximately 7. Okay. How about 10 raised to the negative 3? So base of 10, exponent of negative 3, so we'll say 10 to the negative 3. So 10 cubed is 1,000, so if we have a negative exponent, that puts it in the denominator, so 1 over 1,000. Okay, so if it's base 10, that means it's regular log, so we say log. If you want, you can put the base 10 there, but you want to try to get used to that log means base 10. Log base 10 of 1 over 1,000 is equal to negative 3. All right, let's try some exponential equations here. So log base 7 of 49 is equal to n. We're going to actually be able to solve for the exponent here, and so what we need to do is rewrite base is 7 and the exponent is n, so 7 to the n is equal to 49. So you're asking yourself, 7 to what power is 49? That's 7 squared, or n is 2. Okay. Let's look at another one. Log base 3 of 1 over 27 is equal to n. Okay. Base is 3, exponent is n, so very similar to the previous example. So 3 to the nth power is 1 over 27. So you're asking yourself, 3 to what power is 1 over 27? Well, 3 to the third power is 27, so if we want it in the denominator, that'd be to the negative 3, so n is equal to negative 3 there. Okay, so we're going to look at a couple more basic log equations here. So again, we're going to rewrite the same thing again. Log base b of x is equal to y is equivalent to b to the y power is equal to x, so that's our conversion between log and exponential form. We're going to make the same table with the base, the exponent, the exponential form, and the log form. Alright, so what do we got this time? So we're going to look at log base 2 of n is equal to 4. So our base is 2 and our exponent is 4. So this is 2 to the 4th power is equal to n. So 2 times 2 times 2 times 2 is going to be 16. N is equal to 16. Okay, and one more. Log base b of 36 is equal to 2. Base is b, exponent is 2. We're going to have b squared is equal to 36. Okay. How we normally solve this is we take the square root of both sides, but if you remember from the beginning when we defined exponential, the base was greater than 0 and it was not 1, and same goes for the logarithm. The base was greater than 0 and it's not 1, so that rules out negative 6 as a possibility. So only 6 is going to be our solution here. Okay. So there's some real basic going back and forth between log and exponential form, and a couple of log equations. Real simple equations require you to know how to use the conversion from log to exponential. Now we're going to look at a little more of the fact that logs and exponentials are inverses of each other, so we can think of this as a cancellation or inverse properties. And so that means that base b raised to log base b of x is going to be equal to x. So base b raised to log base b of x is equal to x. That's a cancellation property or an inverse property. And then log base b of b to the x power is equal to x. And so this is no different than addition and subtraction are inverses of each other. Multiplication and division are inverses of each other. So exponential and logarithm are inverses of each other. And so what we're using is composition. F composed with g of x is equal to x, and g composed with f of x is equal to x, using the exponential and the logs as our f and g respectively. Okay, so that's what it looks like generically. So if we're doing e raised to the natural log is going to be x, and then the natural log of e to the x, we'll run into this quite a bit. So natural log of e to the x, ln and e are going to absorb, and we're left with x. 10 raised to log of x is going to be x, and log of 10 to the x will be equal to x. So there's some very common cancellation properties for exponentials. So we're going to look at a couple examples of these, and I'll show you another way of looking at these problems. So we're going to use the cancellation properties here. Okay, so we're going to look at log base 3 of 1 over 27. Okay, so here's one way we can do that. We can say, okay, here's log base 3, and the common base here I want is to be 3. Now 27 is 3 to the third power, but because it's in the denominator, it needs to be a negative. Okay, and then I got those bases are the same, and so I'm left with negative 3. So that's one way of approaching this problem. I'm going to show you another way of doing this. Okay, so log base 3 of 1 over 27 is saying 3 to what power is 1 over 27, and essentially we did the same question there, but that's going to be negative 3, and so there we are. Okay, what about log of 1 million? Log of 1 million, okay? So remember, log is base 10, and 1 million would be 10 raised to the 6th power. And so log and base 10 are going to absorb, and they're going to be left with 6. Okay. So that's one way of thinking about it. Another way, it's very similar. This says 10 to what exponent, or what power, is 1 million, and that's 10 to the 6, or the 6th power. Okay. All right, how about the natural log of e to the 0.03t? Okay. Now here, you might notice, oh, well, e and ln, they're going to undo each other right away. So if you recognize that, that makes it for a very quick problem. Now if we try to answer it in the other way we've been doing it, so this is e to what power? So e to what power is e to the 0.03t, and well, you're probably thinking, well, that's 0.03t. Okay, so there you are. And one more on this slide at least. What's the log base 4 of 64? So if we're looking at log base 4 of 64, if we know some of our powers, 64 is 4 to the third power, excuse me. And you have common base of 4, so those will absorb, and you're left with the exponent of 3 as one method of approaching this problem. Okay? Or we can say 4 to what exponent, or what power, is 64, and that's to the third power. Okay, so let's look at a few more of these. So we're going to look at log base b of b to the 59th. Well, if you recognize you got common bases, those are going to absorb, and you're going to be left with 59 right off the bat. But if we want to write it out in words, this is b to what power is b to the 59th power. Well, that's just 59, so it's equal to 59. How about ln of 1? Okay, so that's actually one of our points in our table. If you remember, we had the ln x, and we used 1 over e, and we got negative 1, and we used 1, and we got 0, and e, and we got 1. So that is going to be 0, because e to the 0 is 1. Alright, so e to what power is 1. And that's the 0th power. So everything raised to the 0th power besides 0 is going to be 1. Okay, so the exponent is 0. All right, well, how about the natural log of 1 over e? Okay, so one way of looking at this is the base of natural log is e. 1 over e can be rewritten as e to the minus 1. Natural log and e are going to absorb, and we're going to be left with the exponent of negative 1. Alternatively, we can say e to what power is 1 over e, and that's going to be the minus 1 power, so that gives us the negative 1 power. Okay? All right. 3 to the log base 3 of 59. Well, you got the common bases there. Those are going to absorb, and we're going to be left with 59. And one more. How about the natural log of the log base 10, natural log of the log of 10 e to the 4th. First thing that's going to happen is log and 10 are going to absorb. And so we're going to be left with natural log of e to the 4th. And then the natural log and the e are going to absorb, and we're going to be left with 4. Okay? So we're going to be switching gears here, and we're going to be looking at solving a few exponential equations. So let me go ahead and speed this up. Okay. So if we're going to solve an exponential equation, the first thing we would like to do is isolate the exponential. And then we're going to try to rewrite so both sides have of the equation have the same base. Then for part 3 it says b to the x equals b to the y if and only if x is equal to y. That's equal bases equal exponent. That's using the one-to-one property of exponentials. And finally, if you can't get equal bases, you'll need to see section 6.6. We need to develop a little bit more. We need to talk about something called the power rule for exponentials. Once we have that, then we can solve any exponential equation. Okay, so we're going to work through a couple examples of solving some exponential equations, and that'll be it for the video. So we're going to solve each exponential equation. And so usually it'll involve, a couple of new steps, and then usually out pops a linear or a quadratic equation. All right, so let's solve 5 times 10 to the n is equal to 50, is it 50 or, no, it's 5,000. Okay. The exponential is 10 to the n, so we want to get rid of that 5, which is connected by multiplication. So we're going to divide by 5, and then we're going to have 10 to the n is equal to 1,000, and 1,000 is 10 to the 3rd power. So now we have equal bases, so we will have equal exponents. And that's it. Alright, let's look at another one. Let's have 4 times 27 to the nth power plus 30 is equal to 1,002. We have to be a little bit careful. Do not multiply 4 and 27 together. Your order of operations says you have to do the exponent first. We don't know what the exponent is, so we can't do that. So let's see. Exponential is 27 to the n, so we want to isolate that. So probably the best thing to do is subtract 30 first. And so we have 4 times 27 to the nth power is equal to 972. Then to undo that multiplication, we're going to divide both sides by 4. And so we have 27 to the n is equal to 243. Okay. Now I know 27 is a power of 3. So up above I'm going to write powers of 3. So 3 to the 0 is 1. 3 to the 1st is 3. 3 squared is 9. 3 to the 4th is 81. I'm sorry, I skipped 1. 3 to the 3rd is 27. And then 3 to the 4th is 81. And 3 to the 5th is 243. So they do have a common base of 3, so we're going to go ahead and rewrite. Okay, so 27 is 3 to the 3rd, and then that's all raised to the nth. And then 243 is 3 to the 5th power. Okay, when I have exponent raised to an exponent, you're going to multiply these exponents. So that's going to be 3 raised to the 3n. is equal to 3 to the 5th. And now we have equal bases. So we will have equal exponents. And so we will have 3 to the n is equal to 5. Divide both sides by 3, and we get n is equal to 5/3. Okay. All right, I think we have a few more examples to go through. So let's see what we got next here. All right, so, oh no, we got a fraction. 1/3 raised to the x is equal to 243. Now, we just saw that 243 was 3 to the 5th. And then, if I'm clever enough about it, I can recognize that 3 to the minus 1 is going to be 1/3. Okay, so 1/3 is 3 to the minus 1. Raised to the x power is equal to 3 to the 5th. Okay, and then exponent raised to an exponent, we're going to multiply the -1 and the x. It gives us 3 to the negative x is equal to 3 to the 5th. Equal bases, equal exponents. Negative x is equal to 5, so x is equal to 5. Not 5, sorry. X is equal to -5. Okay. All right. How about 1/2? I can't see what that is. Raised to the x plus 7 is equal to 2 to the 5x minus 3. Same thing as the number 21 there. If I recognize that 1/2 is 2 to the minus 1, I'm going to have a much easier time doing this. So 2 to the minus 1 raised to the x plus 7 is equal to 2 to the 5x minus 3. So we're working on getting those same bases. Now we're going to multiply the exponents. We're going to multiply -1 times the x and the 7. So be a little careful there. Sometimes students only multiply by the x, and then we get the wrong answer. So it'll be -x and minus 7 equal to 2 to the 5x minus 3. Equal bases, equal exponents. Out pops a linear equation. We're going to add x and add 3, and add x and add 3. So we have -4 is equal to 6x. Divide both sides by 6, and then reduce, and we get -2/3 is equal to x. Okay? So that one's a little more complicated. And we're going to look at, I think, 2 more here. All right, so we got 8 to the x is equal to 2 to the x squared minus 18. So one of the bases is 2 is 8 to the power of 2. It is 2 to the 3rd power. So 8 can be rewritten as 2 to the 3rd, and then it's got an exponent of x. Okay, so there's some powers of 8 over there. Equals 2 to the x squared minus 18. Multiply those exponents. 2 to the 3x is equal to 2 to the x squared minus 18. Equal bases, equal exponents. All right, and let's stop right there. You're in great shape right now. Now, don't go crazy. This is a nice quadratic equation. We don't want to be square rooting. We don't want to be combining 3x and x squared. You name it. Don't go crazy on this now. Okay, it's very simple. We're going to subtract 3x and then factor. So after we get a quadratic, most of the time they're rigged so that they'll factor. Okay, so don't do anything crazy. Okay, so subtract 3x. Remember, we're not taking the square roots. We're not doing some weird combining like terms. We're going to set it equal to 0 and factor it. 0 is equal to x squared minus 3x minus 18. We're still not square rooting. Don't square root. We're not going to do that. Okay, factor. Factors into x minus 6 and x plus 3. And so the roots there are going to be x is equal to 6 and a -3. So we're all done there. So we kind of had like maybe one new step there. And that one new step was rewriting the 8 to the x is 2 to the 3x, and then you got equal bases, equal exponents. Out comes a nice quadratic that you've been solving since the first week of class. Okay. All right, last one here. We have 5 to the x is equal to 3. Those are not common bases. We're stuck. We need to wait till section 6.6 where we have a little bit more theory, so we can't solve it yet. Okay, so we need a log, and we'll come back and revisit it when we're doing section 6.6. Okay. All right, so I think that's it for this video, so we'll see you next time.